video, we're going to work through horizontally launched projectile motion problems. In this first one, it says that a ball is thrown horizontally from the top of a 50-meter high cliff with a speed of 20 meters per second. How far from the base of the cliff will the ball land? So I'm going to start with my sketch. The height of this cliff is 50 meters. The ball is thrown with a speed of 20 meters per second, and this ball will fall to the ground, and we are looking for the how far it will be from the base of the cliff. So we're basically looking for the horizontal displacement. So we're going to start by creating a chart, and in our chart we're going to have all of our variables: delta x, vi, vf, a, and t. And then we're going to have a column for horizontal motion and a column for vertical motion. Okay, so we're going to start with our known. What do we already know in this problem? Well, we know that horizontally that the ball is moving at 20 meters per second. That's how fast it's thrown. And that's we're gonna put that in the VI and VFs. And these are both gonna be the same. Horizontally in projectile motion, the velocity is constant. So I'm just going to draw a big circle right here, and then I'm gonna write in 20 meters per second. Okay, just to remind me that horizontally, that the velocity is constant in projectile motion. I also know that horizontally, there's no acceleration, so that's 0. And I know that the initial velocity is 0 because initially it's not moving up or down. And I know that the height, the delta y, is 50. And I know this is delta x, but for the vertical side, think of it as the delta y, so that's going to be 50 meters. I also know that the acceleration for free fall is going to be 9.8 meters per second squared. And whether it's positive or negative depends on the direction you set as for positive. So for me, I'm going to set right and down as positive. So here are my positive directions, my x and y. It's important to set that up. It is arbitrary, but you just need to stick with it during the problem. And I also like to put an equal sign right here, just to remind me that the time over here will equal the time for the vertical, will equal the time for the horizontal. Okay, so I'm going to start with by solving for the time. Oftentimes with these problems, what we're doing is we're looking for the time. We want to start to figure out the time. By finding out the time, you can figure out the numbers on the other column. Time is what connects the left and the right column. So I'm going to use delta y equals VIT plus 1 over 2 AT squared. I'm using this equation because I'm not using VF. I don't need VF, so I'm looking for the equation without VF, and this is the equation without VF. Now I'm just going to substitute. So this is 50 equals, VI is 0, so that's going to be 0, 1 over 2. A is 9.8 times t squared. And if I solve for t, I get 3.19. I'm going to go ahead and bracket that because I'll use that again. So this is going to be 3.19. This is going to be 3.19. And then now I'm solving for the horizontal motion. Horizontally, it's moving at constant speed, so I can use my constant speed equation, which is delta x equals vt. You could put a vx here just to remind you that we're dealing with horizontal velocity. And the horizontal velocity is 20. T is 3.19, which I just calculated. And if we multiply these two numbers, we get 63.9 meters. So the displacement, how far the projectile lands from the base of the cliff, is 63.9 meters from the base of the cliff. All right, now we'll take a look at another problem. This time we have a ball that's thrown horizontally from the top of a 45-meter high building, lands 60 meters away from the base of the building. What was the initial speed of the ball? Assume no air resistance. So this time we're looking for the initial speed of the ball. Okay, so here's the ball, and we're looking for the speed. I'll call this Vx, horizontal velocity, put a question mark right there. The building is 45 meters tall, and we know that it lands 60 meters away, and it's going to have this trajectory, this path right here. We're going to use our chart to help us solve this problem. We know that the horizontal displacement is 60 meters. The vertical displacement is 45 meters. We're going to make right positive in the x direction and down positive in the y direction. We also know that horizontally the acceleration is 0. Vertically the acceleration is 9.8 meters per second squared, and it will be positive because we made down positive. We also note that the initial velocity is 0. It's not moving up or down initially. And just to remind us that the time for the horizontal equals the time for the vertical. So what I want to do first, like before, is to find the time. And I'm going to use this equation, delta y equals VIT plus 1 over 2 AT squared. Okay, so I'm going to substitute 45 for my horizontal displacement. Initial velocity is 0 vertically plus 1 over 2 times 9.8 times the time squared. Okay, so I'm going to take 45 times 2 divided by 9.8, square root both sides, and I get the time is equal to 3.03 seconds. All right, I'm going to bracket this because I'm going to use this again. This goes into this box right here, 3.03 seconds. This will be the same, 3.03 seconds. And then using this, I'm going to find this number right here, which is the horizontal velocity. I know horizontally the object moving at constant velocity, so I can use my constant velocity equation, delta x equals vxt. Horizontal displacement was 60. My horizontal velocity is what I'm looking for, and the time is 3.03. Okay, 60 divided by 3.03, and I get my horizontal velocity is 19.8 meters per second. All right, one more question. Question number 3. We have a soccer ball that's kicked horizontally from a cliff with an initial speed of 25 meters per second. It lands 80 meters away from the base of the cliff. How high is the cliff? Assume no air resistance. Okay, so here's my soccer ball, and it is kicked with a speed of 25 meters per second, and it lands 80 meters away from the base of the cliff. And this time we're looking for the height. We're looking for the height, which is the delta y. So we're looking for the delta y here. Right? Once again, we want to indicate our positive direction. I'm going to make x positive to the right, y positive down. And this is arbitrary, but you do need to set that up. And when you calculate, you need to be consistent with those directions. Okay, so we know that the horizontal displacement is 80 meters. The acceleration horizontally is 0 because it's moving at constant velocity. Vertically, the initial velocity is 0 and has a vertical acceleration of 9.8 meters per second squared. Because down is positive and the acceleration downward, this will be a positive number. I want to remind myself that the time for the vertical is going to be equal to time for the horizontal. And as usual, I'm going to try to figure out the time. If I can figure out the time, I can figure out the numbers for the vertical column. Horizontally, I know the object moving at constant velocity, so I'm going to use delta x equals vxt. The horizontal displacement is 80. And we were told also one more thing here. We were told horizontal velocity was 25 meters per second. So this will be 25 t. So 80 divided by 25, and I get 3.2 seconds. I'm going to go ahead and bracket that. So I'm going to use that again. I'm going to fill out my chart. This is 3.2 seconds. This will be 3.2 seconds. Okay. And then now I'm looking for my delta y. So I will use my kinematic equation. Delta y equals VIT plus 1 over 2 AT squared. The initial velocity is 0, and the acceleration is 9.8, and the time is 3.2, which I just counted. Make sure you square this number before you multiply by the 9.8 and the 1/2, and we get 50.2 meters.